Let us look at some systems today with some illustrations so that we can understand those systems properly. Okay, let us start with the static and dynamic system. So as we all know, a continuous time system is called static or memoryless if its output at any instant of time t depends at most on the input signal at the same time but not on the past or future inputs. So a static system is what? X of t is there. So this is defined only for t. That means neither it is defined for the past nor for the future. So this type of system is called as a static system or memoryless system, because this system at the instantaneous time of t is equal to t, it works only on that particular time, whereas the value that is present before t is equal to t1 or t2 whatever is not taken into consideration in such type of systems. So such type of systems are called as memoryless. Okay, as the systems have no memory, we also call them as static systems. Similarly, all those systems which do not satisfy this, that means they have a certain value or they predict future, then they are called as dynamic or systems with memory. So this is about a static and a dynamic system. Now let us see some examples. If you see the first example, y of t is equal to ax of t, this is a static system. Y of t is equal to a x of t. This is a static system. So it is defined at a certain time t. Let us say if t is equal to t1, then y of t1 will be equal to a constant multiplied by x of t1 again. That means the value of this particular system is dependent only at a time t is equal to t1. So this is a static system. Similarly, if you look at the second one, y of t is equal to t of x of t plus 6x cube of t. This again is static system, as there is no value of t which actually gives us for t less than that particular value of time, or it is future also. So that means this again is a static system. If you look at the third one is something like this. Y of t is equal to t x of t plus 3x of t square. Okay, now if you look at this system, there are two parts in this. This is the one part plus the other part is this. So the total is y of t. When you look at this type of systems, you see here t square. That means if t is equal to, let us say 2 seconds, then this particular part of your equation gives us the value of this particular component at t is equal to 4. That means we are going beyond the present time, which is equal to t is equal to 2. So that is why this is called as a dynamic system. Similarly, if you look at the other one, y of t is equal to x of t plus 3x of t minus 2. This again happens to be a dynamic system, because the second part of your equation talks about 3x of t minus 2. That is, it talks about the value at t is equal to 2. Okay, so that is again a dynamic system. So these are some of the examples of a static system and a dynamic system. Now let us look at what is called as a time invariant and time variant systems. So what we already know from our earlier sessions, a system is said to be time invariant if its input output characteristics does not change with time. That means a system is such that it is immune to the changes in time. So that type of system is called as a time invariant system. So obviously the other one, if it is varying with respect to time, it then becomes a time variant system. Okay, here we have illustrated this a little. A system h of t is time invariant if x of t, the response of a system x of t is y of t, then x of t minus m will be y of t minus m. That is, y of t is equal to h of x of t, then y of t minus m will be h of x of t minus m. Now let us see this a little carefully here. So what is it I am taking? I am taking a system, okay, having a function called as transfer function which is equal to h of t. The system input, let us say, is x of t. Okay, this is my input to the system, and y of t be the response of your system. Response of the system. Now let us say this x of t is passed through a delay. This is a delay. Okay, this delay is having a certain delay of, let us say now that it is delayed by a certain factor t minus m. Now this is fed to the system. Then here if you see y of t is equal to x of t when there is no delay. Now I am passing the system, I am passing the input through a delay and I am getting x of t minus 1. This happens to be the input of the system having a transfer function h of t. Now the output y of t for such a system is equal to x of t minus m. Okay, so this is how we illustrate this system. Okay, that means what is y of t actually? Y of t is nothing but h of x of t. So this will be y of t minus m if this is x of t minus m. That is what we are trying to tell you here. Okay, so that means it is varying along with the time. If x is varying with time, t is also varying with time. That means there is no change here. So that is why this is called as a time invariant system. Now let us say how do I test a system for time invariance? Okay, what are the different factors under which I test a system for a time invariance? There is a small flowchart here or small steps involved in this. We will follow these steps. Now let us start with the first step. The first step says delay the input signal by m units of time and determine the response of the system for the delayed input signal. Let it be y1 of t. Okay, so what is it we are doing? Taking the input signal, we are delaying it by m units. Then we are finding out the response of that input which is delayed. Then we will get a response, let us call it as y1 of t. That is the first step we have to do. Second, delay the response of system for the unshifted input by m units of time. Let this delayed response be y2 of t. Okay, careful here. So the first one what we have done, we have delayed the input itself. Now second one, what I will do is I will delay the output response. That means the input is not changing, whereas the output I am delaying by a certain time, or let us say certain time m units again, then I am calculating what is my y of t. Then we are calling that response as y2 of t. So one is delayed input, the other one is delayed response. So y1 of t is a delayed input response and y2 of t is the response of a delayed output. Okay, so this y1 of 2 and y2 of 2 we to measure this. Then finally what we will see is we will see whether y1 of t is equal to y2 of t. If they are equal, then system is said to be time invariant. Otherwise system is time variant. So simple. So what I will do is I will calculate what is y1 of t, then I will calculate what is y2 of t, then I will compare. If y1 of t is equal to y2 of t, then system is said to be time invariant. If they are not equal, then they become time variant. So this is how we test a system for its invariance or variance. Let us just illustrate this a little so that you can understand this little better. Okay, the first step. What is the first step? So step 1 says we should delay the input and find out what is the corresponding response to that system. So for us the standard is x of t is our input. Okay, this is my input. Y of t is my response or output. Okay, and h of t or h sometimes is our system. Okay, and the delay is, we are calling it as m units. Okay, it can be milliseconds, microseconds or whatever. So it will be m units. So these are some of the things which we have here. Now first step says I delay my input. So what I will do, my input is this. Okay, x of t. This is my input. This is actually my input. So what I will do is I will pass this through a delay. Okay, so this is a delay element or a delay system. Okay, this will do it by a delay it by a certain m units. Now what will be the output of this system? This output of system is x of t minus m. Okay, x of t and then delay x of t minus m. This is what we got. Now this I have to give it to a system. Okay, so let us pass this through a system. Okay, h of t, or in some cases we can also write as h. Then there will be output to this. This output I am calling it as y1 of t. So this is my first step. So first step you see here, I am taking the input, delaying it, then I am getting a delayed input response. The delayed input response is fed to a system. The system is giving me a certain response, that is y1 of t. We are calling this as y1 of t. So the significant factor here is, this is the important block. This is the first step. In the second step, what are we doing? The input is there, x of t passing through a system h of t, I am getting output y of t. So, what I am doing, this is my response. Now, this we have to delay. So, this is passed through a delay element, okay, having m units, and I am getting an output which is y2 of t. So, here y of t is delayed, here x of t is delayed. X of t delay, I got y1 of t here, and second case I am delaying the output response y of t by certain time seconds of m, then I will get a y2 of t. Now, I have two measurables here, one is y1 of t, the other one is y2 of t. So, if y1 of t is equal to y1 of t, y2 of t, if y1 of t is equal to y2 of t, the system is said to be time invariant. If y1 of t is not equal to y2 of t, then the system is time variant. So, this is how we test a system for time invariancy or time variancy. So, this is the procedure which you will remember. Let us do some problems on this so that you can get this completely understood. Let us see some examples on this. Let us start with the first example. Here it has three parts A, B, C. First example says, state whether the following systems are time invariant or not. Let us start with the first problem. The first problem is y of t is given as 2t x of t. I should find out whether they are variant or invariant. Okay, let us start with the first problem. The first problem says y of t is equal to 2t x of t. 2t x of t. Now, let us see whether this particular system is time invariant or time variant. So, what I have to do is, let us first take the step 1. So, solution. What is the solution? Let us start with the first step. Step 1. Step 1, what is it I have to do? Delay the input by a certain time x of t. So, what I will do is, okay, here we can write x of t I will pass through a system. Okay, this is a delay by a certain m, I will get a value x of t minus m. That is the first step. So, now this we call it, the response to this is we call it as a y of t. So, what will be the output? Let that output be called as y1 of t. Okay. So, the response y of t 2t remains same. Okay. Whereas, what is happening to the input? The input is delayed by a certain factor t minus m. So, this will be x of t minus m. Okay. This is my first equation, let us say, is what we got y1 of t. Then let us see the second case. What is the second step? Second step, I should delay the output. So, the output has to be delayed by a certain factor. Now, y of t is already there for us. Y of t I will pass it through a delay element. Okay, pass it through a delay unit, let us say of m units, then I will get a output. So, this is y of t. What is y of t for us? Y of t in effect is 2t x of t. So, what is the output? The output will be 2 of t minus m x of t minus m. So, let us write down here. So, what is my y2 of t here? 2 of t minus m x of t minus m. This is my second equation. Now, let us see whether y1 is same as y2 of t. As you see here, y1 of t is not equal to y2 of t. So, both are not equal. So, what is the system now? Is system time invariant or variant? The system, because they are not equal, the system is time invariant. Time variant. The system is time variant. Okay. The first y1 of t I got by delaying x of t. That is why 2t is not changed. You see this, x of t is only changed. Now, the whole y of t is delayed. So, it will be 2t of minus m and x of t minus m. So, the system is different for step 1 and step 2. The output response in both the cases differential system is time invariant. Let us see the second example. Here y of t is given as 3 of x of t square. Now again we will follow the same steps, we will not illustrate this again the same diagrams, but what we will do here is we will just put it across. Say that what is y1 of t and y2 of t. What y1 of t, as you all understand, again we are getting it by step 1, and y2 of t we are getting it by step 2. Let us compare both these two. So in short, let me write what is y1 of t. y1 of t is nothing but where the input is delayed by m units. So this will be t square minus m. This is my first equation. Second case is where I am delaying the output y2 of t. So the output is delayed. So this 3x of t square is delayed. So that means the output is 3 of x of t minus 1 whole square. So this is t minus m whole square. y2 of t is equal to 3 of x of t minus m whole square. This is second equation. See from this, y1 of t is not equal to y2 of t. So this system is again time invariant. So this is the second case. Now on similar grounds, you can actually decide how to do Cx of minus t. I leave this to you as an assignment, but again I can give you one hint that again this also happens to be a time variant system. So try this on similar lines, calculate step 1, step 2, then find out whether y1 of t is equal to y2 of t, then you will get an answer. If they are equal, of course they are time invariant. If they are not equal, then they become time variant. So do that as an assignment C. Okay. Now let us see an example 2. The question is almost same. It states whether the following are time invariant or not. Let us start with the first example. Okay, A, B, C, D, E are there. We will see how many we can do in this session, how many we can do as a part of our assignment. Let us see this. Y of t is equal to 2 e to the power of x of t. Okay. Now we have to again find out what is y1 of t, y2 of t. So what is y1 of t here? y1 of t where the input is delayed by a certain time m, and it is a response of that, isn't it? So this will be equal to of e to the power of x of t minus m. So this is my y1 of t. Similarly, how do you calculate y2 of t? y2 of t where I delay my output response. So that again will be, this is the input and I delay it, I will get the same, because this is again a delayed response to the system. Now as you see here, both of them are equal. y1 of t is equal to y2 of t. Then the system is what now? The system is time invariant. Okay. So this is important. So again same steps. Step 1 input delay, step 2 output delay response. We have found out both of them equal. So system is time invariant system. So this is a system which is does not have any effect of time getting delayed. So this is a time invariant system. Let us see the second example. B of second example, y of t is x of t plus c, a constant. So similarly here I can do this is a half a second answer. I mean you can do it in less than half a minute. So y12 is equal to, this is the input delayed, so this will be equal to x of t minus m plus c, because this cannot change. Similarly, what is y2 of t? y2 of t is a delayed response, that is again x of t minus m plus c. As you see here, y1 of t is equal to y2 of t. The system is what? Time invariant. So this is the second example. Let us see the part C of your second example. So where y of t is equal to 3 x square of t. So what is this again? If you look at this, let us calculate y1 of t, then let us calculate y2 of t. Then let us compare y1 of t and y2 of t. So y1 of t is 3 x square of t minus m, then y2 of t is also equal to 3x square of t minus m. So the system is time invariant. So this is the third example. Similarly, what I want you to do is as part of assignment you can do the D and E of this equation. So, that will be simple. The one is a derivative, the other one is integral. That means a system which is giving you an output which is a derivative of the input and certain other parameters. Similarly, have an integral function also with certain other parameters. So, now you find out whether they are time invariant or time variant. Okay, for your information or for your verification something, these two systems are also time invariant system. Let us see another system. It is called as a linear and a non-linear system. So, we have to determine whether a system is linear or we have to determine whether a system is non-linear. So, let us first look out a linear system. As we all know, what is a linear system? A linear system is a system that satisfies the superposition principle. Simple. So, if a system satisfies superposition principle, then it is a linear system. So, what is principle of superposition? The principle of superposition is as follows. So, principle of superposition says that the response of a system to a weighted sum of the signals is equal to the corresponding weighted sum of the responses to each of the individual input signals. Okay. That means, let us say the input is weighed by a certain factor A, B, C or D or whatever. It is weighed by a certain factor. Then the sum of the inputs which are weighed is given to the system, and the system output will also be corresponding to the weighed output responses. Let us say have x of t. There are two parts in this, x1 of t and x2 of t. Let us say, okay, the total response is that. Now, let us say this is weighed by a factor A and this is weighed by a factor B. Now, if x of t is having a response y of t and x1 of t is having a response y1 of t and x2 is having a response y2 of t, then the output will be equal to, okay, a x1 of t plus b x2 of t is what I gave to the system. The system's response will be a y1 of t plus b y2 of t. So, this is the principle of superposition. This is satisfied when the system is said to be linear. So, this is the most important property. Okay, this is how we decide whether a system is linear or non-linear. So, we have put this here, system is linear if h of, that means the function a1 x1 of t plus a2 x2 of t will have a1 h of x1 of t plus a2 h of x2 of t. Okay, here h of x1 of t is y1 of t if we want to express it in terms of the response y1, and h of x2 of t will be the equal to y2 of t. Okay. A system is non-linear if it does not satisfy the superposition principle. So, here we are able to satisfy superposition principle, then it becomes linear. If it is not satisfying, then that becomes a non-linear function. Okay. Then again we will look at the test procedure for linearity, as we have done in the case of earlier, where time invariance of variance. So, let us now find out whether a system is linear or non-linear. What is the test procedure? Let us look at the first step. Let x1 of t and x2 of t be two inputs to system h of t, and y1 of t and y2 of t be the corresponding responses. So, we have given x1 of t and x2 of t system, and we are getting corresponding outputs as y1 of t and y2 of t. That is, x1 of t is having a response y1 of t and x2 of t is having a response y2 of t. Now, let us consider another signal x3, which is nothing but a1 x1 of t plus a2 x2 of t. That means, it is weighed, the input is weighed by a certain factor a1 and the other input x2 of t is weighed by a certain factor a2. So, this is a combination of these two. Let us y3 of t be the response to x3 of t. Then check whether y3 of t is equal to a1 y1 of t plus a2 y2 of t. If equal, the system is linear, otherwise the system becomes non-linear. So, what are the steps? Let us take two signals x1 of t and x2 of t with the corresponding outputs y1 of t and y2 of t. Then take a signal x3 of t, which is a weighed sum of these two signals. It is x3 of t is a1 x1 of t plus a2 x2 of t. Then you find out output. So, corresponding output for x3 of t will be y3 of t. So, y3 of t must be equal to a1 y1 of t plus a2 y2 of t. When this condition is satisfied, the system is said to be linear. If this condition is not satisfied, then the system is said to be non-linear. Let us see some examples again on this. Okay, as we have done in the earlier case, let us find out whether the following systems are linear or non-linear. Well, let us start with A, B, C, D, E are there. Let us see how many we can do in this session. Okay, let us solve this problem. Y of t is given as t x of t. So, let us take two signals. What are they? x1 of t and x2 of t. With the corresponding outputs, what are they? y1 of t corresponding outputs and y2 of t. So, these are the corresponding outputs. Then again take another signal x3 of t. What is that? We said x3 of t is a weighed functions of these two. That means it is a1 x1 of t plus a2 x2 of t. So, this is my output. So, what is y of t here? y1 of t here will be equal to t x1 of t and y2 of t will be equal to t x2 of t. So, this is the corresponding system responses that we have keeping here. Now, x3 of t is a1 x1 of t plus a2 x2 of t. Okay. So, what is y3 of t? y3 of t is nothing but the transfer function of these x3 of t. That means I can expand this. So, that will be equal to h always will be there. Let us say this will be equal to a1. What is x1 of t for us? T x1 of t plus a2 t x2 of t. So, what I will do is I can break this into two parts. So, I will write this as a1 t x1 of t. Okay. This again h here, that means the system function which you are putting it here. The second one is h of a2 t x2 of t. Now, if you see this is nothing but y1 scaled by a certain factor. So, this is y1 of t for us and this is y2 of t. Now, this is summation here and this is scaled by a factor a1 and this is scaled by a factor a2. So, this is my y3 of t. Now, if you see the output y3 of t is a1 y1 of t plus a2 y2 of t. So, this is completely satisfying the principle of superposition. So, the system is said to be linear. So, the system is a linear system because the x3 and y3 the additions are same. So, there is a superposition principle that is being completely implemented in this problem. So, this is a linear system. Okay, let us see the second B of your example again here. So, we have a system y of t is equal to x of t square. Let us break this. Let us say there are two parts in this. What are these parts? You have x1 of t that is equal to x1 of t square, then you have x2 of t that is x2 of t square. Okay. So, x1 and x2 will have a corresponding system responses that is equal to y1 of t and this having corresponding system response equal to y2 of t when it is passed through a system h. That is what we all know. Okay. Then let us say x3 of t is nothing but x1 of t plus x2 of t, where x3 and x2 are scaled by a factor, let us say a here and b here. So, this is my x3 of t. So, what is this in equation a1? A x1 of t is how much? x1 of t square plus b x2 of t square. So, this is my first equation and this is equal to x3 of t. Similarly, let us find out what is y3 of t. y3 of t is the system response of x3 of t, that is this is equal to system response of a x1 of t square plus b x2 of t square. Now, we will bring out a here out, okay, and h of x1 of t square is nothing but y1 of t. So, this will be equal to y1 of t, okay, plus b y2 of t though, and this is equal to y3 of t. Now, if you look at these two equations, it is again satisfying superposition principle and then the system is said to be linear. Now, the system is in fact a linear system. Let us see the C of example here as we are following, as we have done A, B. Now, let us see the C here. Now, C equation is y of t is x square of t. Earlier it was x of t square, now it is x square of t. So, let us see again the corresponding these things. We will write down here directly. X3 of t is nothing but a x1 of t plus b x2 of t. Okay, corresponding. So, what will y3 of t will be? You see here this is a squared function. So, this will be equal to a x1 of t plus b x2 of t whole square. So, when I expand this, I will get like this. This is the h of it again. A square x1 square of t plus b square x2 square of t plus 2ab x1 of t and x2 of t. So, when you look at this y3 of t, see here this is okay, this is okay, but you have an extra terms which is coming here. So, the output response is not satisfying the superposition principle. That is why the system is non-linear here. So, this is a non-linear system. Earlier it was linear because it completely satisfied your superposition principle. Now, if you look at this here, it is not satisfying superposition principle. The system is said to be non-linear. Now, what I want you to do is, let us look at D and D, try to solve them, okay, and find out whether they are linear systems or non-linear systems. So, you can just find out as an assignment, you can see whether this is D and D are linear or non-linear. But I request all of you to follow the procedure which we are being introduced in this session, where we said there are certain procedures, test procedures what we called it. So, test procedures may be followed accordingly, and then you try to solve this. Once first problem you do with test procedures in a complete format, then once you understand the gist of that, then probably you can do it orally in your mind and then just put across the answers directly. Then let us look at another type of systems which we have already seen, that is a system is causal or a non-causal system. So, what we know already is a system is said to be causal if the output of the system at any time t depends only on the present input, past inputs and past outputs, but does not depend on the future inputs and outputs. So, this is a causal system. So, causal system is a system which takes care of all types of conditions. Okay, and in fact, because of these conditions which we are trying to define a causal system is said to be a real system, or in other words a system which is practically implementable. Okay, if a system output any time depends on future inputs or outputs, then the system is called as a non-causal system. Okay, it depends on something in future, then that becomes a non-causal system. The causality refers to a system that is realizable in real time. As I have told you, any system which is realizable in real time or which is practically implemented, which can be practically done, is a causal system. An LTI system is causal if and only if the impulse response is 0 for t less than 0, that is h of t is 0 for t less than 0. Now, take a linear time invariant system, that is an LTI system, and let us look at the LTI system. The LTI system is said to be causal if h of t 0 for t less than 0, that is a system response. This is called as a causal system. Okay, these examples we will see a little later on how the examples can be done. We will see once we finish off this. Okay, then we will look at stable and unstable systems. So, what do we know about a stable system? An arbitrary relaxed system is said to be BRBO stable if and only if every bounded input produces a bounded output. Examples of bounded input signal are step signal, decaying signal, impulse signal. Unbounded is ramp and increasing exponential signals, of course, because there is no limit to the input. The input is not bounded, so output definitely will not be bounded. So, the examples are, you can just talk about a small step signal, or you can talk about a decaying signal, or you can talk about an impulse signal which is present only for a certain time. These are all bounded, whereas unbounded exponential signal which is increasing, and a ramp signal, as you all know, is always increasing with respect to time, they are unbounded. Now, what is the condition for a system to be BIBO, that is bounded input bounded output, for a LTI system? For LTI system, the condition for BIBO stability can be transformed to a conditional impulse response h of t. For BOBO stability of an LTI continuous time system, the integral of impulse response should be finite. That means when integrate between minus infinity plus infinity h of t dt, that value should be less than infinity. So, this is how you define LTI system, whether it is BIBO stable or not. So, take the response h of t and integrate it from minus ∞ plus infinity, the value of that must be less than infinite. So, that will be equal to this must be less than infinity. So, the system is said to be BIBO stable, and if it is diverging, that is the value is not converging h of t, then the system is said to be unstable system. So, in this session what we have done is we have looked at different systems which you already studied. We have gone a little bit deep into them. We have illustrated some of the points here.